Okay, so so here is the model that we're looking at. So I'm going to assume that there are time bounds. You know, this is real. Now we're talking about real time, you know, clock time. So we assume that there is a bound of a C1, which is the minimum step time that a process can take. So a process cannot run any faster than C1, and it cannot run any slower than C2. So between C1 and C2, each process will take a step. And it's non-deterministic where in that range the step takes place. And we'll use big C for the ratio of C2 over C1. So for synchronous models, big C is 1. For asynchronous models, it's infinite. And so this is, here we're looking at models that are kind of in between synchronous and asynchronous. Yeah?
C1 and C2 has to be the same for all the processes?
Yeah. So, but within that, you know, they can pick any time they want. So one process can run faster than another one, but they can't run more than C times faster. And then there is a D, which is the maximum time it takes to deliver a message. So we know that if you're supposed to send me a message, and it will show up within time D after you send it. And so we assume that C1, C2, and D are known to whoever it is who's designing the protocol. So imagine that one process takes Q steps. So how do I know that another process has taken Q steps? Well, in real time, it has to take less than Q times C2 time, because C2 is the slowest it can move. So you multiply that by Q, so I know that in real time, Q times C2, it must have taken Q steps. So that means, since I don't actually have a clock, the only thing I can count is my own steps. That means that I have to, if I take Q times big C steps, then I know that another process must have taken Q steps. So that the only way I have of making sure that someone else has taken a certain number of steps is by taking C times that many steps myself. That is, I know that by the time I finish taking Q times big C steps, the other process must have taken Q steps. Also, if the other process takes Q steps, then it must have taken more than Q times C1 time, because C1 is the fastest it can go. So that means that I must have, in that time, I must have taken more than Q divided by C steps. So there's a range, you know, how many steps, if I take a certain number of steps, then it could be that the other one might have taken C steps. If I take another number of steps, then I know for sure that it has. So there's a range, there's a time range of the number of steps I might take that while the other process takes Q steps. So in some sense, this says how much do you know about what the other processes are doing based on how many steps that you've taken. Is that clear?
The numbers are somehow confusing me. So both in this slide and the previous one.
So here, so if I'm taking Q steps, then C2 is the
That has elapsed, yes.
yeah, that's the slowest step time.
Okay.
So this is the real time that must have happened.
Okay.
So if I want to make sure that this much real time has happened, then I have to take that many steps.
In the worst case, the blue guy moves every small C1
Yeah.
step, and so
Yeah.
it's C2 over C1.
Yeah. Yes. Yeah. So if so you know, it could be that I'm moving slowly and the other guy is moving fast, or vice versa. And those are sort of the two extremes. So how long does it take to figure out that another process has crashed? So if a process crashed, then I can tell because it didn't send me a message. So if I'm expecting a message and I time out, then I might start out thinking that process is live, but when I don't hear from it, when your phone doesn't ring, it's me, then then I know that the process is crashed. And how long do you have to wait? Well, you have to wait for at least time d.
You have a common 0?
Yeah. I'm assuming that there's a common 0 here because it only gets worse if you don't. And so the adversary that we fabricate is going to do that. So for time d, then you have to wait at least d over c steps, which is real-time d times c. So your timeout here is time d, the message delay times the c, which is the measure of asynchrony. So that's your worst case timeout in this model. So there's so if my protocol says at time 0 you send me a message, and I don't get it in that much time, then I know that you've crashed, but that means I have to wait. So I can detect failures in this model, but you have to wait a long time. Now in the synchronous model, we can do consensus in C rounds, where C is the minimum core size. Because basically, it was the protocol that we did before, where everyone in the core does standard synchronous consensus and then tells everyone else. So in the semi-synchronous model, there's a really naive way to do consensus, which is we simulate the synchronous model in our semi-synchronous model. So we can simulate synchronous consensus. So on each round, you broadcast your messages, and then you time out. So I send a message. I wait until either I've heard from everyone or enough time has elapsed that I know that they've crashed. So that is worst time C, the size of the core, the big C, the measure of asynchrony. And that's really bad. We don't like that.
There's a D there.
Oh,
C times D times C.
yeah. You're right. That's a typo. Because the timeout is the yeah.
So each step you wait D times C.
Real time, yeah. And that's bad. So there's a known lower bound, a famous paper that appeared in the 80s, 90s, 80s, which basically said that actually if you're more clever about it.
This is APLS.
Yeah.
So this is not topological.
No. This is an actual algorithm and actual operational arguments and so on. So which says that there's a lower bound, which says that you have to have at least one timeout, which is the C times D, and everything else you can run basically as fast as possible. Meaning you just you send messages which take time D to arrive. So that's the lower bound, and that says that you can in some sense have a single timeout for everyone.
The surprise is the upper bound, really not the lower bound.
Yeah, the upper bound is the same thing, only with a factor of 2. So it's off by 2. And that's a really mystical algorithm. That, you can convince yourself it works, but how this was thought of is a mystery to me. I think one of the co-authors is here, so.
And the gap is still open?
I think it's still open, except for bizarre values, ratios between C, D, and F. The C, the core size. Yeah, there's still a lot. Surprisingly, it hasn't been improved. I mean, I think your work in Michailidis is kind of almost the only.
Yeah.
There's very little follow-up.
Yeah, it was a hard model, and what happened was when they introduced failure detectors, people stopped worrying about this. Yet another reason to dislike failure detectors. Okay, so I'm going to introduce a fast adversary who does the following. So it's going to run in a sequence of rounds. And each round takes exactly d, the maximum message delay time.
Now trying to prove the lower bound?
Oh, no, this is the lower bound that was already proved. So we're going to do a different lower bound. We're going to do a lower bound for conductivity and set consensus, which will imply the earlier lower bound. But just for background, there's this known lower bound for a consensus. So each round is going to take a time exactly d, and we're going to run processes as fast as we can. And what happens, though, is that we're going to delay messages until the end of a round. So processes are going to take steps. They're going to send messages, but we're going to delay the messages till the end of the round and then deliver them all at once. And we're going to fail exactly k processes in each round. So here, too, we're going to try to postpone k-set agreement for as long as possible. We're going to try to keep the protocol complex as connected as possible. So here's what it looks like. So in each round, since round takes time d, and d we'll assume is significantly longer than the step time, we're going to divide the round into micro rounds, where each micro round takes time exactly c1. So it's like we have a kind of a synchronous system here. We're going to take d and we're going to divide it by c1, round it down to get mu micro steps, micro rounds per round. And so this is, in each round takes time d. And all the messages are going to be delivered at the end of the round, because the message sent here must be delivered by the time we get there. So to make life easier, we're going to deliver every other message that was sent before the end of the round there. So here we have, say, 2 micro rounds, finishes 1 round in time d, then we start the next round. So now we're going to talk about failures. So we're going to kind of encompass failures in something we'll call a failure pattern, which is just kind of a table of who's failed. So here, P0 failed at micro round 0, and P1 basically kept going. So we'll say that f of 0, so f applied to a process number tells you the round in which it failed. And here, P1 is still alive when it finishes. Mu, remember, is the number of micro rounds per round. So it's still alive and well, so we'll give it f of 1 is a mu. So this is basically an integer valued function where everything goes between 0 and mu. Now, again, a failed process might send a message.
You fill them in between as well?
So all we know is that we'll assume that it may drop dead in between this micro round and that micro round. So we'll just assign it to whichever micro round it does not take a step in. So it's an integer valued.
But also between, like you'll have mu minus 1 or minus 2 or something?
Yeah,
or
yeah.
Just fail either at 0 or at mu?
No, we fail in the middle too. So that, in fact, that's important because what happens is, so here, this guy fails in micro round 1, but it also sends a message from micro round 1 before it fails. So it's like the synchronous model. At the time you crash, you might still send a message, or you might not. So here, blue gets a message from red at micro round 1, even though it failed at that round. Or it might not send a message. You might get a message from 0, but not from 1. So again, there's some uncertainty. If I get a message, if I don't get a message on micro round I, then I know that it failed either at I or at I minus 1. I don't know which one. So for any failure pattern, there's a possible view of that failure pattern, which is the one process's view of what happened, which is not exactly what might have happened. So here, blue sees that red was silent at micro round 2. Green never provided any messages, and purple it assigns it mu because it was never silent. Now, in fact,
How does blue know what micro round?
well, because when you send a message, you label it with the micro round you're sending it from. So at the
one at 2 and he didn't. He was supposed to send 1 at 2 and didn't.
Yeah. So every micro round you send a message, the adversary batches them up and then delivers them all at once, and then you go through them.
But the messages say what
Yeah.
round it was.
Yeah. So here is one possible view of a computation, or it could be that red was silent at 1 instead of silent at 2. So what happens is that, so we'll use, say, bracket F are all the views compatible with a particular failure around F. So big F is what actually happened when they actually crashed. And this F sub j is J's view of what happened, which says that either you see F minus 1 or you see Fi if Pi fails, and you see mu otherwise. So you might get a message from the process in the round that it failed. So I might get a round I message, and your arm might not, or vice versa. So we have that same kind of one round ambiguity about when things fail. So we fix the failure pattern F.
The method then contain at which round you are?
Yes, it does.
So how come we don't know?
Because when I fail, I might send you something with a round 1, but I might crash before I send Hagit a message with round 1. So you'll say, oh yeah, I have a round 1 message, and Hagit will say, I got a round 0 message. So there's that one last gasp uncertainty before the process fails. And so what is this? Well, this is each non-faulty process. So we have tau, because we are actually failing processes here. So tau is a set of non-faulty processes here. So it's independently assigned a view compatible with F. That is, it has its ideas about when everyone failed. And it might not agree exactly with F, but it's only off by 1 at most. So it might agree or it might be off by 1. And these are all assigned independently, so it's a pseudosphere. So what we get is, again, the union of pseudospheres, because we look at all the failure patterns where tau is non-faulty. So we fix a set of non-faulty processes. We look at all the failure patterns that don't fail any of those processes. And then for each one of those, we look at all the views that are compatible with that. So we have a bunch of big sets here. So the one-round protocol complex is the double union of pseudospheres. Fearsome thing. First we did a single pseudosphere, then we did a couple where we had unions of pseudospheres, and now we have a double union of pseudospheres. What does this look like? Well, we look at each face of codimension k. That is, on each round we fail k processes, and so we look at all the different ways we can fail k processes. Once we have one of those, then we have all the ways that, all the failure patterns that don't fail here. We have all the views that are compatible with that. So we have, this big double union of, sets and sets of sets and so on. And here the theorem is that for r less than this quantity in any simpler, for this many rounds, RSS is shellable of a dimension at least this. And mercifully, I'm not going to go through the proof because it's exactly like what you saw, except that we have 2 levels of union, and so it's a lot of chasing through the partial orders and total, chasing through the total orders and showing that things are shellable and so on. And there's nothing particularly different from what we did. There's a lot more of it, and it would take some time, and I don't think it would be very enlightening to do that. But it's in the chapter notes on the web page.
What do you get out of this? I mean, no. Yeah, so you have it there.
Well, so the corollary is for this many rounds, there's no semi-synchronous message passing protocol for case-set agreement in real time less than R times D, where D is the message time. But that's not very interesting because it's too short. So this is way shorter than the time lower bound for doing consensus. And so, this isn't, this isn't yet what we're looking for. So now what I'm going to do is I'm going to take this execution and stretch it and pull it to make it a lot longer. So here's a round, which remember it takes time d, the time it takes to deliver a message. Remember it's divided into micro rounds, and each of the messages sent are delivered at the end of that round. So this is how the adversary works. So we put these together, and we have a bunch of rounds, and then there's the final round, and each of these takes time d. And so this part here we have R times d. Remember, R is the bound for doing set agreement. And so what we proved was you can't do set agreement after this amount of time. So now we're going to kind of bargain a little bit. And so what I'm going to do is I'm going to look at the round after we prove that you can't do case-set agreement. So here we have we show there's no case-set agreement. So let's look at the micro rounds after that. Well, all the messages sent in that round are delivered at the end of that round. So in fact, we can move our deadline almost one more round further because nobody's learned anything since then. So at the time all these messages were delivered, you couldn't do a case-set agreement. So if we wait till epsilon before you get the rest of your messages, you still can't decide.
You do learn the time has passed.
You know the time has passed, but if you could have decided here, then if you couldn't decide here, you could have decided here. Because you haven't heard anything, you haven't learned anything new. The only thing you know is that,
it's passed, and
yeah.
it's some kind of knowledge.
But if you look at the protocol complex here, any map here you could have pulled back here because there's no non-determinism here. You're just, you get a bunch of messages, you wait for some amount of time. If I could decide here, then I could have made the same decision before. Because I haven't learned anything.
The reason I worry is that it seems as if you don't, I mean, if you still have another failure left that you are going to use in this round, I'm not worried. Because, okay, this I can imagine. But if you are going to squeeze out the extra d times c, which is what you are going to do, you are striving to do now, without a failure. So one thing is that this will be a minor improvement on the lower bound for consensus, which has d minus 1. So kind of we need to keep one failure for the last round.
Oh, yeah, no, we have plenty of failures left.
Okay. So if you still have one more failure,
Yeah, yeah. But I haven't got there yet. All I'm saying is that you go to the next round, you wait until epsilon before any messages are arrived. You still can't decide. Because the fact that the time has passed without getting any messages doesn't mean anything because you don't know whether any failures have occurred. It could be that everyone else has failed. It could be... And again, the reason is because since you haven't received any messages, there's a one-to-one correspondence between your state at d minus epsilon and your state at the start of the round. So now what we're going to do is I'm going to fail all but one process. So one by one, I'm going to crash everyone but a single solitary survivor. Then what I'm going to do is I'm going to take this and I'm going to slow down the survivor and run it for a long time. And this one survivor doesn't see any difference because it can't tell whether it's taking steps quickly or slowly. In either case, it doesn't hear anything from everyone else. That is, until, because we're stopping epsilon before the timeout time. So I'm going to time out C times D minus epsilon. And so the claim is you still can't do case-set agreement here because it's indistinguishable from the other execution where everyone was healthy and running quickly. So it's just a stretching. So the corollary, and this one is the actual result, is there's no semi-synchronous message passing around for case-set agreement in time less than core size divided by k minus 1 times d. These are the rounds plus a single timeout.
You don't need to factor in the bookkeeping for the failures, like you needed lots of failures. I mean, how this fits with the survivor set.
So you still have to keep I think that works.
I'm sure there are numbers for which it works, and I see the minus 1 there, and I'm relieved, so to speak.
Yeah. So so the claim is this bound is almost tight. Same reason as before. We have here's an example. We have a core of size C. We divide them up into C over K. We run the ADLS protocol. Each one individually runs the ADLS protocol. And then they tell the others. So that's why this is. So that's the adversary stuff. So what time is it now? 5 minutes before 4. Okay, so I think what I'll do is I'll give you a very quick preview of what we'll do 2 weeks from now, and then let you go. So this is more of a teaser than. Okay, so first thing so all the general tasks that we considered so far are basically colorless tasks in the sense that your identity doesn't really matter. That any process can pick anyone else's input or take anyone else's output. So there's a kind of a symmetry requirement here. And so what I'll do is I'll give you an example showing you why these two kinds of tasks are fairly different. Why the things we proved so far aren't strong enough to do what we want. And then next time I'll give you the more general theorem for the case. So here, the basic theorem for colorless tasks, which we did before, is here I've given input complex, output complex, and a relation with the star, meaning that they're colorless. This has a wait-free read-write protocol if and only if there's a continuous map from the input complex to the output complex carried by the relation. So that's a nice simple property. It would be nice if everything in the world works like that, but unfortunately when you start introducing asymmetries, I think life gets much more complicated. And so what I'm going to do is I'm going to give you a counterexample showing why this doesn't apply to colorless tasks, and then we'll talk about this later. So this is an example of a task that is invented to cause problems. So I'm going to call this an hourglass task for reasons you can see. So it's fixed input. Every protocol has only one possible input, and it may or may not participate. And the output complex looks like this. And the rule is that if you're the only one participating, then you end up here. You know, if you're here, you end up here. If you're there, you end up there. If you're there, you end up there. If it's only P and R, then you have to end up somewhere along here. And P and Q is symmetric. So if you end up here, then you have to end up along that thing. And the reason this is not colorless is because Q and R are different. If Q and R participate, then you have to end up somewhere along here. So you can see that it's sort of symmetric along this axis, but it's not symmetric along there. So the claim is that the hourglass satisfies the conditions of our theorem. So if the theorem worked for colored tasks, then we would have a wait-free read-write solution to this task. But in fact, there is no wait-free read-write protocol for the hourglass task. So this is a kind of a counterexample to our theorem. So first I'm going to claim that this satisfies the conditions of the theorem, that there is a continuous map from the input complex to the output complex carried by delta. And that's fairly simple. This is our input complex. That's our output complex. So one is homotopic to the other. You just take the waist and you squeeze it together, kind of like a corset, and there you go. That's a continuous map. So if our theorem worked for colored tasks, then we'd be done. So how do we know that there is no wait-free read-write protocol for it? Well, I'll reduce it to something that we already know is impossible. I'm going to show you that you can solve two-set agreement with the hourglass task. So if I had a wait-free read-write protocol for hourglass, then I would have a wait-free read-write protocol for two-set agreement, but we know that's impossible. So here is the protocol. So the first thing you do is you announce what value you want. Then you run the hourglass task. And so here are the possible outputs. You know, I've labeled each one with a integer so you can tell them apart. So the idea is you look in the announce array. So I announce my value. I run the protocol, and I end up on some vertex here, depending on who else participated. And so if I end up here, then I pick the value p. If I end up here, I pick the p. If I end up here, if I end up down here, then I pick either r or q. If I end up here in the middle, then I look in the announce array, and I know that either r or q or both will have a value there. And I pick either one of those. And so all you need to do is check that on every simplex, at most two different values are chosen. And you have to convince yourself that there will be a value there. So if I'm here, then that means that I'm p and I ran, so I have a value. If I'm here, then p must have run because I'm in the sort of PR range. So I can only be here if p is participating. And if p is participating, then it already wrote its value, and so on. And same for q and r. Here, it's ambiguous. It could be that r is participating but not q, or q and not r. But either way, one of those two is non-null. And no matter which choice I make, I have only two values. So that says that you know, if I can solve this, I can solve two-set agreement. I can't solve two-set agreement. And yet this satisfies the conditions of the colorless theorem. So that says that the colorless theorem, you know, really relies in a fundamental way on the fact that the task is colorless, that your ID doesn't matter. And this task is not colorless, so the theorem technically doesn't apply. And this shows that, in fact, there's a reason it doesn't technically apply. So the question is, you know, what went wrong here? And one direction is OK. So if this color task has a read-write protocol, then there is a continuous map. And that argument works the same. The other direction is the one that fails. It says that if there is a continuous map carried by delta, then it's not necessarily the case that a protocol exists. So the answer is that we need a stronger condition than this to make everything work. And the condition is going to be basically that this map has to be a color preserving in a sense that we'll define next time. And so then what we'll do is we'll show that, what we did was we say, well, if we have this map, then we take a simplicial approximation to the barycentric subdivision, iterate, and then barycentric subdivision is repeated snapshot, and that gives us a protocol. What went wrong is that this is not a color preserving map. So you can run the barycentric agreement, you could end up with somebody else's output. And that's perfectly okay for a colorless task, because by definition, anybody's output is good for anyone. Any output is good for anyone. But that's not the case for a colored task. And so the output you end up with might be someone else's output, and you might not know what to do yourself. So that's the heart of the problem. So I'll give you a different kind of map that has to be satisfied next time we do this.